Hi everyone, this is the last video for Chapter 8, Acids and Bases. Let's get started. This entire video is going to teach us how to manipulate the equilibrium constants that we learned in the last video. First problem says, let's find the pH and composition of a solution containing 0.0200 mole benzoic acid in 1 liter of water. The first thing you have to realize is that to find the pH, you need the concentration of H+. We can find the concentration of H+ if we use the acid dissociation equation. We have the Ka of this reaction, it's right there, 6.28 times 10 to the negative 5. And we also have the reaction, so we can use our knowledge of what's going on here to figure this out. First thing you have to realize is for every mole of A-, that's being the benzoate that's being formed, 1 mole of H+ is being created. It's a 1-to-1 ratio. So what you could do in all of these weak acid type problems, you're going to be able to do the same thing. You can make up this little table which shows what the initial concentration is of all of the species and the final concentration of all of the species. So HA is in equilibrium with A- and H+. F stands for formal concentration. They actually gave you the formal concentration of this reaction. If you remember, it is 0.0200. That is the formal concentration of this solution. So that's what you would put there. But at the beginning, you have HA, right? You have only that solution, and then you have none of the products, because initially nothing has happened yet. At the end of the reaction, you have concentrations both of A- and H+, and they happen to be the same, right? Because it's a 1-to-1 ratio, so we can put X for both of those. And the final concentration of the HA would be F minus X, the formal concentration minus whatever dissociated. Because remember, these are weak acids and weak bases, so they're not going to completely dissociate, they're only going to partially dissociate. So you have to figure out, at the end of the reaction, you still have some HA left in there, but how much? If we put this table or this stuff that we've written down into an equation, into our Ka equation, it can look something like this. At the end of the reaction, you're going to have X, X, and then HA will be F minus X. You can use this to figure out what we need to know. Like I said, we can substitute F for 0.020, and the Ka was actually given to us. So if we take this and we multiply both sides by 0.0200, as I'm showing you right here, and then collect like terms, you'll see that you end up getting what looks like a quadratic equation. So x squared plus 6.28 times 10 to the negative 5x minus 1.256 times 10 to the negative 6 equals 0. For these weak acid and weak base problems, you're going to have to use a quadratic equation to get your answers. So if you don't remember how to do them, you need to start remembering now. This is the general formula of a quadratic equation. It's negative b plus or minus b squared minus 4ac, all under square root, divided by 2a. If you go ahead and plug in all of the numbers that we got, and by the way, this would be your a, this would be your b, and this would be your c. If you go ahead and plug in all of those values that we got and solve for x, you're going to get 1.09 times 10 to the negative 3 molar. X, remember, is your H+. If we go back over here, you'll see that the X was your H+ and your A-. Okay, so now we have the concentration of your hydronium ions at the end of that reaction. One thing I want to note is that there are 2 answers to the quadratic equation. Those are your 2 roots. We're going to go ahead and disregard the negative root because it doesn't make any sense, right? How can we get a negative concentration? So we just go ahead and disregard it. All we keep is the positive root. So X is equal to 1.09 times 10 to the negative 3 molar. Just as a check, if you have time to do this, let's say in your exam, you should check that the answer that you got for X makes sense if you plug it back into the Ka equation. So for example, if you plug in 1.09 times 10 to the negative 3 back into the original Ka equals x squared over f minus x, that answer you should get should be the Ka, which was 6.28 times 10 to the negative 5. And if you do that, you will get that number. So that's a check to make sure that the answer that you got for your quadratic equation is correct. So now, from the value of x, like I said before, we can find the concentrations of everybody in that solution at the end of the reaction and the pH. Since we know that H plus and A minus are both equal to X, we know the concentration of those two species. And the concentration of HA, which is the weak acid, the original weak acid, would be F minus X, which is 0.020, the molar concentration of the solution, minus the amount that dissociated, which is obviously your X. That ends up being 0.0189. So now you have the molarities of all species at the end of the reaction. And of course, with the H plus concentration, you can find your pH, which ends up being 2.96. At the beginning of this conversation, we said that for every mole of A minus that was formed by dissociation of that weak acid, the HA, 1 mole of H plus is created. In other words, the concentration of A minus is equal to the concentration of H plus. For reasonable concentrations of weak acids of reasonable strength, the contribution of the H plus from the acid is much, much greater than the contribution from the dissociation of water. In other words, we said that the concentration of H plus is 1.09 times 10 to the negative 3 molar, which means that if we were to figure out what the concentration of OH is in there using the equilibrium of water, you would get 9.20 times 10 to the negative 12 molar. I got that by just solving for OH in the KW equation. So H plus from HA dissociation is equal to the concentration of the A minus. And that's what we got, right? That's the 1.09 times 10 to the negative 3. And H plus from water dissociation, so just from regular water dissociation, is equal to the concentration of OH from water dissociation. And that is equal to 9.2 times 10 to the negative 12. The assumption that we made at the beginning that H plus is derived mainly from HA is really, really good, because 1.09 times 10 to the negative 3 molar is much, much greater than 9.20 times 10 to the negative 12. In other words, this dissociation is mainly happening because of that weak acid, not because of water dissociating. You have to remember that all these things are interconnected. Weak acid, weak base, you add those two together, we get the dissociation of water. So you have to make sure that when you make these assumptions, that the dissociation of the actual acid is much, much greater than the dissociation of pure water. So now what if I wanted to ask you, what's the fraction of dissociation of that weak acid? This is easy because this is just a percent. So you take the concentration of A minus of the conjugate base, which we found is 1.09 times 10 to the negative 3, and then you divide it by the concentration of the entire solution, the original solution, 0.02. If you do that, you get 0.054. So this acid is indeed really weak. It actually only dissociated 5.4%. Obviously, I just multiplied that 0.054 times 100. What is the take-home message here? Whenever you're faced with a weak acid problem, realize that the concentration of H plus is going to be more or less equal to the concentration of A minus. And that is going to be your X. So the equation that you're going to use for weak acid problems is right there. It's X squared divided by F minus X, where F is the formal concentration of the original solution. Let's try to find the pKa now of a weak acid. A 0.100 molar solution of hydrozoic acid has a pH of 2.83. Find the pKa for this acid. So now this is a little bit different, because I'm giving you the pH and I want you to find the pKa. This is really simple. All you got to do is, like I said here, take it step by step. You know the pH, so what does that mean? That means that you know the concentration of the hydronium ions, the H plus ions. So to find the H plus concentration, I'm going to do 10 to the negative 2.83, which gives me 1.48 times 10 to the negative 3 molar. Since I know the equation I'm going to use is Ka is equal to x squared divided by F minus x, I know that my H plus is my x. I also know what my formal concentration is. So basically I plug 1.48 times 10 to the negative 3, square that, divided by 0.098. How did I get 0.098? I took 0.100 minus 1.48 times 10 to the negative 3. When I divide those two numbers, I get 2.22 times 10 to the negative 5, which is my Ka. Obviously, to get the pKa, I just take the log of that, and that ends up being 4.65. So whenever we do weak base equilibrium, it's almost exactly the same. We already have learned how to do it. Now, the only difference is that where you put the x is now an OH, not an H plus. So just remember that. And of course, you have the equation for the weak base is a Kb, not a Ka. But everything else is going to be exactly the same. So if we did an example that read, find the pH of a 0.0372 molar solution of the commonly encountered weak base, cocaine. So here I'm showing you the reaction and I'm giving you the Kb. So my general equation here is going to be B plus H2O is in equilibrium with BH plus OH. I know that these two over here are going to be my X's, and I know that my final concentration of my B, of my base, my weak base, is going to be 0.0372 minus X. I plug that into the Kb equation, and I'm going to get X squared divided by 0.0372 minus X. I go ahead and do my long and lengthy quadratic equation, and I end up getting an answer for X that's 3.10 times 10 to the negative 4th molar. Remember that this X is not H plus, this X is OH. So we have to use the Kw equation, the equilibrium constant for water, to find the concentration of H plus. So I'm going to put 1.0 times 10 to the negative 14th divided by the answer that I got, 3.10 times 10 to the negative 4th. That ends up being 3.22 times 10 to the negative 11th molar. I take that and place it into my pH equation. pH is equal to the negative log of H plus, and that ends up being 10.49. And that is a reasonable pH for a weak base. If I then wanted to know the fraction of association for my weak base, it's the same thing that we did before. Now it's just the weak base, right? So we're going to put the answer that we got, 3.10 times 10 to the negative 4th, because that was the concentration of that weak acid conjugate at the end of the reaction, divided by the formal concentration of the original weak base, which is 0.0372, divide that, and you're going to get 0.0083. Turn that into a percent, and you'll see that it's only 0.83% of the base has actually reacted and associated itself. All right, guys, we're going to do more problems like this in class, obviously, but please practice. There's a lot of problems that you can try that are in the book. Practice, because this is definitely going to be on your test. All right, guys, see you later.